In this video, we're looking at a trapezoid approximation for a really problematic function. So I recently put this on a calculus quiz just thinking, well, sine x over x doesn't have any elementary antiderivative to write down, so it's a good candidate for a trapezoid approximation. And what I didn't notice as I wrote this down is that the left end of the interval has an undefined point. If I plug in x equals 0, I end up with a 0 in the denominator, and that point can't be in the domain of the function. So the problem that arises is after we set up our trapezoid sum, whatever technology you're using, whether it's a calculator or a computer algebra system or a programming language, is going to throw an error when you try to sum up the areas of all the trapezoids. So what we're going to do in this video is set up the trapezoid sum, and then I'll show how we deal with that one trapezoid all the way on the left-hand end that's causing an error because there's a domain issue at that point. So in the picture, we're actually looking at our 1,000 trapezoids. Those are just so skinny that all we can see here is kind of a rough haze of vertical lines. And when we get into making adjustments at the left end of the interval, we're going to go ahead and zoom in on this graph and get a little clearer view of what's going on. For now, we start setting up the approximation. And I like to always start these things out with a few pieces for the setup before I write down a final sum in sigma notation. So first, I'm going to write down the subinterval width. We're taking the interval 0 to pi over 2, which has a width of pi over 2, and we're dividing it into 1,000 subintervals. So I end up with a delta x, that's the interval width, of pi over 2 divided by 1,000, and it's going to be more convenient to write that as pi over 2,000. Next, I like to write down a formula for the cut points. Those are called the x sub i's. And the ith cut point is just I steps to the right of the starting point. So we can write this in general as x naught plus I delta x. This time the starting point, meaning the left end of the interval, is just 0, so we don't have to write that. And then we have I delta x, which is an I times pi divided by 2,000. So next I'd like to write down the formula for a trapezoid sum in general, and then we'll plug in the details. So the idea is that we slice this thing into 1,000 trapezoids, and then we add them all up. So there's our sigma notation. And we're going to start our sum from I equals 1, and then I'll talk about the upper limit in just a minute. And the area of a trapezoid is the mean of the left and right heights of that trapezoid. I'm going to write this as f of x I minus 1 plus f of x I. So the f of x I minus 1, that's a height at the left-hand side of a subinterval. And then the f of xi is the height at the right-hand side of a subinterval. So we have the mean of the two heights now, and then we have to multiply by the width of each of those thin trapezoids, and that's delta x. So what about the upper limit of the summation? It's wise to play around with the formula here and just make sense of the endpoints. Like if I sub in I equals 1, this left-hand height is going to be f of x sub 0. In other words, our function evaluated at the left end of the first subinterval. That happens to actually be the problematic point that we're going to run into in a second. And then f of xi would be f of x1. That's the height at the right end of the first subinterval. And when I get to the end of this summation, I've got to have 1,000 trapezoids. So I know this upper limit is 1,000. Just because that's the only way to get 1,000 terms in my sum. And just double checking my subscripts here, that would give me f of x 999 for the left side of the last trapezoid, and f of x sub 1,000 for the height at the right end of the last subinterval. So everything looks good here, and then we can plug in the details for our sum. For just a minute longer, I'm going to pretend that I don't see the domain error, because that's exactly what happened to me while I was writing down the solution to this problem during my calculus quiz. And then, of course, the technology gave me a heads up that I had missed something important. So we need to plug in the details about our function here. I need to write down f of x sub I minus 1. Just a little note here. This works just like function notation. If xi is I times pi over 2,000, then xi minus 1 is just I minus 1 times pi over 2,000. So we need to evaluate our function, that's the function we're integrating here, at this value of x. So I end up with a sine of I minus 1 times pi over 2,000, all divided by xi minus 1, which again is I minus 1 times pi over 2,000. Okay, so that's my left-hand heights at each subinterval. Then I need to write down the right-handed heights. So that's our function evaluated at x sub I. So I'm going to get a sine of I times pi over 2,000, all divided by I times pi over 2,000. And don't forget to put on the width of each of these trapezoids. I have this tiny width that we call symbolically delta x, and every one of these trapezoids has to be multiplied by that. That's pi over 2,000. Now, one really convenient thing to do at this point before you try to plug this into a computer algebra system or whatever utility you prefer is that every term has a 1/2 in it and every term has a pi over 2,000 in it. So we could factor out a pi over 4,000 out in front, and that just makes it easier to type everything in. So now you have to imagine me as a math teacher 10 minutes into a calculus exam, getting all of this plugged into a utility and finding an error. And I actually got the error first from a TI-84 calculator, and then I double checked with Python. So this is what my failed attempt looks like. I plugged in all the details about the sum. Notice that I factored out the pi over 4,000 out in front just to simplify things a little. And we're just taking the sum of all those terms. Hopefully you can recognize here that I have my left height in this first chunk, and then I have my right height in this second chunk. And then we're summing it all up as I goes from 1 to 1,000. Now Python has this interesting quirk that the end of a list is always one digit less than the number you type in there. So this is actually the sum from 1 to 1,000. And we get an error popping up that says invalid value encountered in scalar divide. In other words, there was a division by 0. And at first I thought Python was just mocking me when it said nan, and I had to look that up because I'm really new to Python, and that stands for not a number. So our approximation failed, and of course this is when it dawned on me we're looking at a function that's not even defined for the first trapezoid. So of course we're not going to give up on this, we're going to look for a workaround, especially when we're just approximating something. Like the answer doesn't have to be perfect, we just have to be able to approximate it to arbitrary precision. So let's just take a second to zoom in on the problematic rectangle. And we notice some really beautiful moire interference along the way as we're zooming in here. And notice that the function is so flat when we get really close to x equals 0 that these trapezoids all look like they're literally rectangles. Well, they're not literally rectangles, but they are very, very close to being rectangles. And our problematic trapezoid is the leftmost one there because its left height is not defined. But notice that that left height really, really looks like it's equal to 1. And that's not just some coincidence. We remember from Calculus 1 that we had this really important limit that we proved by using a geometric construction, that the limit as x goes to 0 of sine x over x is equal to 1. In other words, that y value is arbitrarily close to 1 as x becomes arbitrarily close to 0. Now, because we're doing an approximation, we don't actually have a problem here at all. We can just say, okay, let's move 1/trillionth of a unit past x equals 0. And the height is going to be extremely close to 1. It's going to commit an error so small that it's irrelevant for our purposes. And we can just replace the left height of the first rectangle with 1, and it's going to be indistinguishable as a decimal approximation to this integral. So that's our fix. We just need to split off the first trapezoid. So we're going to go back into our summation notation and just make a quick modification here. I'm just going to take my eraser tool and just kill this really important limit. I'll put a link up at the top if you want to see how that was derived in Calculus 1. And I'm going to kill that 1 from my starting point because what I'm going to do here is split off the first term of this summation and then make my starting point I equals 2 for the summation notation. So we have to write the I equals 1 term manually here. So that's going to be the area of a trapezoid. Again, that's the mean of the heights at the left and right ends multiplied by the width. And what we're saying here is we commit an infinitesimal amount of error if we just replace the left-hand side with a 1. So that's done. And then the right-hand side, again, this was the I equals 1 term. The right-hand side is going to be a sine of pi over 2,000, simply replacing the I with a 1 there, divided by pi over 2,000. And the width of that trapezoid was pi over 2,000. All right, so I had to stop my class while they were taking this calculus quiz, and I said, hey, there's a problem with the first trapezoid because its left height is actually undefined because we have division by 0. Here's an idea for a workaround, and then I just turned this workaround into a 1-point bonus if people applied it successfully. So now we're going to make some modifications to what we plug into Python, and here's the corrected code. So what I did here is I switched it to starting my trapezoid sum from I equals 2. Again, terminating at 1001 means the sum ran all the way through I equals 1000. Then I defined a new guy called trap1, and that's just the area of the first trapezoid. Again, we're committing just an infinitesimal amount of error by saying the left height of this guy is equal to 1 because we know the limit as we approach that point is equal to 1. All right, and then the second piece in these parentheses is the height at the right end of that first trapezoid. And then notice that I did the factorization here where I gathered the 1/2 and the pi over 2000 width of this trapezoid out in front and wrote that as pi over 4000. So now we display trap sum, that's the sum of 999 trapezoids, plus the first one that we had to handle manually because of the division by 0 issue, and we get our final approximation for the area under this curve on 0 to pi over 2. So on my quiz, I had asked for an approximation to the thousandths place, and so we're going to round this to an approximate area of 1.371, and we've got our final answer. And I was actually pretty happy that the problem turned out to have this complication in it because it made the problem a little deeper than these trapezoid approximation problems normally are. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.